I'm going to talk to you today about something called a Lagrangian Quasi-Cobordism, which isn't really a real thing. We made it up, but I will tell you what that is. So let me write down. So this is based on joint work with Josh Sabloff, Vela-Vick, and Mike Wong. Okay, and this talk is roughly going to go in 4 parts. So the first part, I'm going to tell you a little bit about Lagrangian Quasi-Cobordisms. And then I'm going to define Lagrangian Quasi-Cobordisms. We'll talk a little bit about its metric and monoidal properties. And time permitting, we'll talk about decorating. Okay. So let me start with some definitions. So you might be already familiar with a Legendrian knot, what that is. So I will not define that, but I will say what it is. So Legendrian knot is a smooth knot, which is everywhere tangent to some contact structure. And for me today, the contact manifold that I care about is going to be R3 with the standard contact structure. And I'm going to define what a Lagrangian cobordism is. So given 2 Legendrian links, lambda minus and lambda plus, they're going to live inside of my contact manifold. An exact Lagrangian cobordism, it's going to be, I'm going to denote it L. It's going to live inside of the symplectization of R3. With the symplectic structure where alpha is the one form that gives me my contact structure. And I'm going to require, I guess, 3 things. The first thing is that it has cylindrical ends. So if I look at L on the negative end, what I see is just a cylindrical guy that looks like my knot times this infinite interval. I'm also going to get a cylindrical end on the positive end, which is just going to look like my positive link. And the third thing that I'm going to require is this exactness. So there exists some function f from L to R such that df is going to be e t alpha when restricted to L. And there's one extra thing that I'm going to require, and it's that f is constant on the cylindrical ends. Having this fourth thing is necessary if I want to consider like DGA maps. It's necessary if I want to basically be able to concatenate these cobordisms. I need to require this. This is because I'm defining this cobordism between links. If I had this just on knots, this would not be necessary. All right, I think Chantrain looked at some of the weird consequences if you don't have this requirement, and you immediately get all kinds of misbehavior. So we just put it there. Yes?
I just might have missed, is the projection on the R coordinate proper? Like, is it compact in each R3?
Yeah, let me draw a picture. So this is what I picture in my head, right? So I have my copy of R3. I have my other copy R3. I have some Legendrian knot living inside of these copies of R3, and then between them, I have my cobordism L, and then on the ends, I just have cylinders.
And that middle part is compact, right?
Yes. Sorry, I misheard you. Right. Okay, so what else do I want to say? If I have a Lagrangian cobordism, I'm going to denote this with this symbol. And if the genus is 0, then this is called a Lagrangian concordance. And I'll denote it, with a 0 up there. All right, and that's the definition. So now let's talk about some of the important properties or qualities that I know and care about for these Lagrangian cobordisms. So the first property is that when I think about the smooth four-ball genus of a knot, so that is the minimum genus of any surface that is bounded by a knot. The surface is in the four-ball, the knot is in the boundary S3. Then if I think about Lagrangian cobordisms, these are always going to realize the minimum genus. So if I compare to like smooth topology, right? If I have a cobordism between two smooth knots, I can always add just like more handles to that cobordism and I will get more genus. But with Legendrian knots and a Lagrangian cobordism, that can't happen. That cannot happen. So these are always going to be genus minimizing. What else? The relationship, so this, thinking about this as a relationship on Legendrian knots, I know that it's reflexive. This was proved by Chantrain. So if I take a Legendrian knot and I perform a sequence of isotopies, I will get a Lagrangian cobordism between where I started and where I ended. I also know that it's transitive. So basically I can concatenate the compact part of these Lagrangian cobordisms, and then I'll just have whatever cylindrical ends on the ends, and those are still going to be Lagrangian cobordisms. And what else do I know? Well, actually, I know that these are not symmetric. And I think if you study a lot of symplectic geometry, you're pretty comfortable with things not being symmetric. But this is very different from like the smooth world, where if I have a regular cobordism, I can just flip it around, right? And I get another cobordism. So there's this phenomenon in smooth topology where having concordances on knots actually gives me this amazing group structure on my knots. And I don't get that here because I don't have that this relationship is symmetric. Yes.
So what the genus minimizing thing, is that something that's like completely clear, or I don't know, classical? Like, what is the proof of that?
I am blanking right now.
Oh, that's okay. But it's not like obvious. Is it?
You can sort of compute the Euler characteristic of the Lagrangian.
Right, yeah.
Using really.
Oh, okay. So it's okay.
Yeah, so there's a formula.
I see. Okay,
Yeah.
then it's not like anything. It's not like any four-theory thing. It's just like a statement about the classical invariance of Legendrian.
Yes.
Yeah. Okay.
I'll say what that statement.
But then a smooth one is clear that a smooth one.
You don't know that Euler characteristic formula for a smooth thing.
But then, well, I'll ask about this later. It sounds like it might be a little complicated to explain.
Let me say a little bit more about like not symmetric, and then I'll talk about classical invariance and less classical invariance. So this was proved by Legendrian as well, but what's currently wide open is the question, is it anti-symmetric? So if it's reflexive and transitive and not symmetric, natural question is it anti-symmetric? The answer is no idea. In fact, it is not known even like if I have a double concordance to and from the unknot, does that thing have to be the unknot? In fact, we don't know any Legendrians that aren't the unknot and are cobordant to the unknot.
Is the other direction always true? Is there always some cordons from the unknot to anything else?
It depends on the unknot. So, but yes, well, if you're allowed any kind of, no, if you only allow this one. No, if you only allow this unknot. So here's like a straightforward reason why. Lagrangian Quasi-Cobordisms are obstructed by classical invariance of Legendrian knots. So what's your favorite classical invariant of the Legendrian knot? TB, yeah, okay. So if I have, let me see, I'm gonna make sure I write this down correctly. So TB of the knot at the bottom is equal to TB of the knot at the top minus, I think, the Euler characteristic of L. I might be getting this wrong signs, or I might have flipped these, but they're related by the Euler characteristic. And also I have that the rotation numbers, if your favorite classical invariant is the rotation number, have to be the same. Right. But it is true that if you allow like stabilizations, then you can always find a knot below, like that is coborded to any, sorry, an unknot that is coborded to any knot if you allow that unknot to have stabilizations. All right. I will go over here. Okay, some more properties. And secretly I'm giving you actually one more invariant type property. So they're also obstructed by non-classical invariants. So in particular, they're also obstructed by the stable team isomorphism class of lambda minus, of the Legendrian DGA of lambda minus and lambda plus. So the first non-classical invariant is this thing called the Chekhov-Eli-Ashford DGA or Legendrian DGA. While the DGA is the differential graded algebra is something that we can compute given a Legendrian knot. And while that DGA itself is not an invariant of Legendrian knots, if we consider the classes of DGAs up to stable tame isomorphism, that is a Legendrian invariant. And that's how we get all of these things. Like if we take the homology, that's going to be an invariant. If we count the augmentations, that's going to be an invariant. All of these ruling things and other stuff that you hear about, they all sort of are properties, if you will, of the stable tame isomorphism classes of the DGA. So in particular, the main source of obstruction is the fact that this behaves functorially over Lagrangian cobordisms. So if I have a cobordism from lambda minus to lambda plus, then I have a map that goes from the DGA of lambda plus to the DGA of lambda minus, right? And this is going to be a DGA map here. And so I'm going to have augmentations being sent to augmentations and all kinds of other nice behavior here. So if I can break this map, then I can show that there's no Lagrangian cobordism. Okay, and then one other property that I wanted, actually I have how many more properties that I want to mention? 3-ish more properties that I wanted to mention. So one other property is that these cobordisms can be what we call decomposable. And what decomposable means is that they are built or they're constructed out of certain pieces that I know, right? So those pieces are going to consist of Legendrian isotopy, they're going to consist of Legendrian isotopy plus index 0, what we call birth moves. And what these look like is I have a max TV Legendrian unknot at the top and nothing at the bottom, right? So locally I'll have sort of one of these coming into fruition and that'll be a birth move. So this is the positive end, this is the negative end. And then what we call index 1 pinch moves. These are saddle cobordisms where in the positive end, I see a ribcord and the bottom, I see a pair of cusps. So this is going to look like this on the bottom and the top. And I'm going to have some kind of saddle. And I can see here that I have sort of a ribcord that I've pinched down. Right, so what I actually know is that if I have two knots and they're related by this, or they're related by this, or they're related by this, then they're Lagrangian cobordant. Completely open question is, are all Lagrangian cobordisms decomposable? That's completely open. We have some conjectured counterexamples. We don't really have a good way of proving that they're not decomposable. And another way of thinking about this question is you can think of it as the Legendrian version of like ribbon, right? So are all slice knots ribbon. Are all ribbon. There's
It's the wrong crowd to ask.
yeah. There's a big open important question. Yeah, I think so too. In like smooth topology, which asks if all slice knots are ribbon, and you can think of this as like a Lagrangian version, which is are all Lagrangian cobordisms decomposable, and both are open. You can ask, maybe you remember this recent result of 6-page result of Ian Agall that shows that all ribbon cobordisms are partial orders, sorry, that ribbon cobordisms form a partial order on smooth knots. You might ask like a version of that question here. So like if I restrict decomposable knots, then do I get a partial order? That's also open. So lots of sort of easily stated questions about this relationship where we do know the answer in the like version within the smooth world. We just don't know the answer here, right? So that's another question. So let me say a couple of things that we do know, because I've said a bunch of things that we don't know. So here are 2 more properties. The first was shown by results of Miranda, Trainer, and Jan. And it's that if I have 2 Legendrian knots and they have the same rotation number, so if what I know is that there exists, actually let me call these ones lambda 1 and lambda 2. Then there exists a lambda minus such that lambda minus is coordinate to both lambda 1 and lambda 2. So you can think of this as like a lower bound result on Legendrian knots. And then sort of following this, there is a result by my collaborators which says that actually there's also an upper bound. So if I have 2 Legendrian knots with the same rotation number, then I have some upper bound that works equally for both of them. Right. A little bit about the construction here. So the way that this works is that they show that basically in R3, you can perform a series of decomposable moves that gets from any Legendrian knot to a possibly very stabilized unknot. So there's like some sequence of isotopy and pinches and birth that gets you down to a very stabilized unknot. And if you sort of, and you can always add more stabilizations as you go down. So if you stabilize, if you get something really stabilized below here, you get something even more stabilized below here, then you can like stabilize all the way down to get to there.
It's just like a knot with a lot of cusp.
Yes, very squiggly and knot. And then what they showed in R3, it's a little bit more complicated if you think about other contact manifolds. In R3, what you can do is basically reverse the pinches. So you have, let's say, some sequence of pinches that gets you down to here, and some sequence of pinches that get you down to here. Let me draw these with different colored arrows.
So isn't stabilizing makes you go down in this order, so you have cobordism going the other way?
Yeah, stabilizing is way to go down. Okay. And well, there's a way to go down and get something more stabilized, maybe is the correct way to say that. And so what you can do is you can sort of keep track of what pinches you did to get down to this lower bound, and then keep track of what pinches you get down to get to this lower bound. And then sort of once you get here, do the equivalent of those pinches this way. and do the equivalent of these pinches over here. And that will produce some sort of upper bound. And this is in sort of R3 where this happens. Yes.
Can you read kind of or estimate the number of pinches you have to do from the rotation number?
You can read it based on the number of crossings that you see in the, so the way that they do it, basically they say if you have this kind of crossing, you can do this sequence and that gets rid of that crossing. Oh. So what they're doing is they're getting rid of all of the crossings in the knot. Okay, so with all of that, that's sort of all I wanted to say about Lagrangian cobordisms without the quasi. And so now what I'm going to do is I'm actually going to define what I mean by Lagrangian quasi-cobordism. So, by the way, these boards are really nice. They're like very luxurious to write on. Okay, so part 2, I'm going to define a Lagrangian quasi-cobordism. And the way that I'm going to do this is by first defining what I'm going to call a Lagrangian join, which probably guess what it is. So a Lagrangian join between two Legendrian knots, lambda minus, or sorry, lambda 1, lambda 2, where the same rotation number is exactly the information that I get by finding an upper bound. So is sort of this cobordism plus whatever this upper bound is plus this cobordism. So these three pieces of information form what I call my Lagrangian join. Right? And then Lagrangian quasi-cobordism between 1 and lambda 2 is, or actually let me call this lambda n, where they have the same rotation number, is then just a sequence of Lagrangian joins that go from 1 to the end. So you can think of this is going to be smoothly a cobordism between these two knots, right? It's going to be a smooth cobordism between these two knots, and you can think of it as like somehow like a piecewise Lagrangian cobordism between these two knots. So let me just.
Zigzag of Lagrangians.
Yeah, it's like a zigzag, exactly. All right, right, and one more thing. So a Lagrangian quasi-concordance is one with genus 0. Right, so that means that every single piece is like a trivial cylinder. And actually, let me add an important word that I forgot. Actually, the way that I wrote this is not just a word, it's a phrase, is one of these where L1 and L2 are connected. So I'm going to require that the individual pieces of the Lagrangian join and therefore the Lagrangian quasi-cobordism always be connected. And the reason why I want that, or why I need that, is the following. Okay, so if I don't require this, then I'm allowed to do the following, right? I can have some Legendrian knot here with some strand sticking out here, and I can perform, or I can construct a Lagrangian cobordism from this to this guy. By just doing a simple birth move, right? So this consists of plus some bunch of cylinder, well, plus some cylinder, let's say, if this is a knot. And then I can then do this, right? I see that there's actually a red cord here between these two things, so I can pinch. So then I get down to here, which means that I can doubly stabilize and stay in the same Lagrangian concordance class. And that's bad because that's because of the following reason. So if I have a smooth Legendrian, then I can sort of get as close as I want. Sorry, if I have a smooth knot, then I can get as close as I want to it by just adding a ton of zigzags to my Legendrian, right? And I can just get as close as I want to that smooth knot if I'm allowed to add as many zigzags as I want. So if I allow myself this, where I can just keep adding zigzags, then this relationship becomes not uninteresting, but it becomes smooth cobordism, which this is like a very convoluted way to define smooth cobordism if I'm going to do it this way, right? So if I want this to be distinct from smooth cobordism, somewhere between Lagrangian cobordism and smooth cobordism, I'm going to require that my individual components of cobordism be connected. And that gets rid of that problem. And so let me talk a little bit about why you might be interested in doing this. So as I said before, this relationship Lagrangian cobordism, it's reflexive and transitive, but it's not symmetric. So it's not an equivalence relation. But if I sort of define this new relationship, this quasi-cobordism relation, then this is an equivalence relation. It's definitely symmetric, right? And so now I have an equivalence relation on Legendrian knots. And so I can think about sort of the same thing that I would in the smooth category where I take concordance classes. I can take Lagrangian quasi-concordance classes, and I can ask sort of what are the properties of this thing that I've created, right? In the same way that
any idea if I connect two guys, lambda one and say lambda one and lambda something by zigzags. There should be an equivalence relation that I replace zigzags with zigzags.
Yes, yes, exactly.
And then there should be sort of a minimum number of zigzags.
Yes, yes. So, well, a minimum number of zigzags. Well, I can always just reduce it down to one zigzag, right? Because I can always take the upper bound between the two knots. The sort of interesting thing the other thing that I can do, which I will talk about when I get to part 3, is that I can come up with this notion of minimal genus, where I look at all of the possible zigzags and I think about the minimum genus over all of those zigzags. And that gives me a distance between two Legendrian knots. And then I can think about what are the metric properties on Legendrian knots using that.
So going up, taking the join increases genus, is that right?
So that's a good question. So a question which we don't actually know the answer to is if I take just one piece versus if I take lots of little pieces down here, can I actually get less genus by going like a bunch of little zigzags versus this? We don't have any examples where we've constructed something with less genus by going down this way. Yes.
And like pull back augmentation in Legendrian DGA, is there a condition in a cobordism which would let you push them forward?
So one of the decorations that I talk about here is like we can ask that instead of thinking about just Legendrians, I think about Legendrians with an augmentation. So the objects in my sort of top and bottom are now a Legendrian with an augmentation, and then I require that the DGA map relates, like sends all of these augmentations to each other.
Sure, sure. No, I guess I was just wondering whether there's like some kind of special cobordism which you could invert, which are better than inverting all of them, which would be a big invariant. You don't know. Okay. Thank you.
Okay, but I still haven't told you like one basic thing, which is this actually more sort of free than Lagrangian cobordism? So let me prove that to you. So theorem, there exist Legendrians lambda minus and lambda plus, which are Lagrangian quasi-concordance, but not Lagrangian concordance. I think this also is sort of fun to talk about because I can talk about a couple more pieces of technology that we have and properties that we know about Lagrangian cobordism. Yes?
Are they also not Lagrangian cobordism?
Yes. Yes. Okay, so the proof of this is like fairly straightforward, but it sort of, I don't know, demonstrates like a couple of interesting tools that I have in my belt when I'm talking about Lagrangian cobordism, so I think it's fun. So let me consider two particular Legendrian knots. The knots that I care about here are going to be this knot called, the max TV representative of the mirror 946 knot, and the max TV representative of the 12 non-alternating 7, 6, 8 knot. You don't really have to care about what these knots look like. I just want to write them down. But the point is that these are both slice knots. Not just slice, they're both Lagrangian slice.
Like, what does it mean to be Lagrangian slice?
It bounds a Lagrangian disk.
Okay.
Or
slice knots that don't bound Lagrangian?
Yes. So the smallest slice knot is like the stevedore knot. And that one, while it is smoothly sliced, is not a Lagrangian slice. I think it has genus 1 or something. Okay, so.
Oh, and is there like surgery reasons why we like to know if things are like Lagrangian slice or not?
Another way of saying Lagrangian slice is saying cobordant from the unknot.
Okay.
If you want.
But I mean, like slice knots, like in smooth topology, like are important because they bound smooth disks and not smooth disks. So like.
Yeah, that's a good question. And like one of the questions that we had when we were thinking about like what are the properties of this quasi-cobordism was like, okay, is there any notion of like torsion here? Like if I take 2 knots and I take their connect sum, do I then get like something that is quasi-cobordant to the unknot or some unknot or anything like that? And the answer is we don't. We can show that there are certain knots that don't, and I will write that down in a second, but in general, we don't really know if there are any sort of inverse or torsion results on Legendrians. Yeah, lots of questions. So these knots are both Lagrangian slice, which means that they are Lagrangian quasi-concordant, right? I can stick an unknot between them, and so I get sort of, let's see, trivial concordance, then the unknot. And here I put a trivial one here as well. Another good question, right, is I picked going up for my joins. What if I picked going down for my joins? Is that different? But for now, let's just stick with this.
How do people find like Lagrangian slice knots? Do they just like check all the slice knots?
Yeah, I think the strategy is to like check the slice knots, check the classical invariants, and then try to construct something. Yeah. Well, no, if you check the slice knots for their classical invariants and the classical invariants work, like they're the right ones, then you know there has to be some like cylinder joining that to the unknot.
Oh, okay.
So that's all.
So it's just the classical invariants are sufficient.
And then if you want to construct it, you can try using the decomposable moves. And like for instance, with the 946, that one definitely works. There's like, I think one pinch gets you there. Okay, so these are both Lagrangian slice, so they're Lagrangian quasi-concordant. And now the question is, are they Lagrangian concordant? Right, is there cylinder joining them? And for that, I'm going to tell you a little bit about stuff that we know about Lagrangian quasi-cobordisms. Again, so here is a theorem that was proven by Cornwell and Sabloff. And it says if I have a concordance from lambda minus to lambda plus, then I can take any satellite of lambda minus with any sort of satellite pattern. And this is going to be concordant to the satellite of lambda plus with the same satellite pattern. All right, so that means that if I think about these two knots, I can take,
what is the satellite?
So I'm going to take n copies of the knot, and then I'm going to n parallel copies, and then I'm gonna take like a little pattern at the top that like joins them together. So for instance, let me just do an example of the unknot. I can take a satellite of this by specifying a pattern and like the number of strands. The number of like parallel copies. So for instance, if I say that this is my pattern, right? Then I can take a 4 copy of this unknot and then just add this pattern in here. And that would be a satellite. No, I didn't. I'm okay. Okay, so what I'm going to consider is the Whitehead double, the TB twisted Whitehead double of both of these knots. So I'm going to take 2 copies, and then I'm going to add this pattern in. So let this be the satellite of 946 with the pattern like that. And then I'm going to do the same thing. Mirror 946. And this one's going to be mirror of the 12 and 768 with the same pattern. Right? Then if these two are concordant, then these two are concordant. Sorry, if these two are concordant, then these two are concordant, right? So let me now obstruct the concordance here. And the way that I'm going to do that is with a computer because I'm lazy. And in particular, I'm going to use the following result from Han, which says that if I have this concordance plus some extra conditions, which I'm not going to go into, then I have the following thing on what's called the ruling polynomial, these knots. So if you think about sort of smooth knot invariants, you have a lot of these invariants that come from these sort of skein relations, right? So like if you think about the way that you think about, or the way that you might define the Jones polynomial or the Alexander polynomial, you do it with like the skein relation thing, and then you end up with some kind of polynomial as your invariant. So the ruling polynomial is like the closest thing to that we have in Legendrian knots, but it actually is like deeply related secretly to the stable tame isomorphism classes of the DGA. So, right, so we have the following property on the ruling polynomial. So, if I think about lambda minus here, and I take the ruling polynomial on Q 1/2 minus Q minus 1/2, then this is going to be less than or equal to the ruling polynomial of lambda plus at Q 1/2 minus Q minus 1/2, where Q is a prime power. And because this is the ruling polynomial, I can compute directly from a front diagram of Legendrian knot. I have programs that do this for me. And so what I'm going to do is I'm going to feed it both of these knots. It's going to give me a ruling polynomial, and then I'm going to put different values of Q in and see if I can break it. So when I do this,
so this is for arbitrary Q.
For Q of prime power.
Like for arbitrary prime powers?
Any prime power, yes. I'm always going to have this inequality. So when I do this, what I end up seeing is that the ruling polynomial of did I call them minus and plus? That was probably bad, but okay, that's fine. When I take this ruling polynomial, I get the inequality this way. And when I take this ruling polynomial, I get the inequality the other way. So that means that they're not Lagrangian concordant, even though they're Lagrangian quasi-concordants. Okay. Great. So I do know then that this Lagrangian quasi-concordant thing is sitting somewhere between, this Lagrangian quasi-cobordism thing is sitting somewhere between smooth cobordism and Lagrangian cobordisms. And the next thing that I'm going to do is, indeed, I'm going to define this notion of, oh, I should have put this one up. I'm going to define this notion of minimal genus. So we are now at part 3. All right, so if I have any two Legendrians, let's call them lambda 1 and lambda 2, with the same rotation number, I can, any two Legendrians with the same rotation number. I can associate a number which is minimum genus over all quasi-cobordisms between lambda minus and lambda plus. And this gives me a metric. So now what I have So I have a metric monoid on, I guess, Legendrian knots. On classes of Legendrian knots up to Lagrangian
All right. What is the addition? Did you already say what the monoid structure is?
So the monoid structure I get from connect summing over these Legendrian knots, and then the metric is the new thing which I've added here, although I already said something about it before. So now I can ask sort of questions like, what are the properties of the metric monoid? And let me list, how much time do I have? Like 10 minutes? Let me list some of these properties and prove some of them, but not all of them. So first of all, for any Legendrian lambda, there exists some Legendrian lambda n, so that lambda n is n away from lambda. The proof of this is really simple. It's the following. So I know that the genus of the cobordism between the unknot and the following knot where I have 2n plus 1 crossings here, but this has genus n. How do I see this? Well, how many pinches does it take to get down to the unknot? Well, I can pinch here and here, and that's a genus 1 cobordism that gets me 2 crossings less, right? And so if I do 2n pinches, then I get a genus n cobordism to the unknot. So if I want, if I start with lambda, then I can just connect some with this guy, and I get something that is genus n away from lambda. So take lambda, connect some this guy. Here is another theorem that also has a quick and easy proof. So for any lambda, there exists a sequence of lambda I, so that if I have a Lagrangian cobordism, then it achieves the minimum genus.
Oh, yes.
So I constructed the cobordism, so it must be the minimum genus. So for any lambda, there's a sequence of lambda I, so that G L of lambda I is 1 for all I. But lambda I is not quasi-concordant to lambda J for any J. So in other words, if I'm thinking about this like metric monoid as a graph, then I have like infinite valence. And right, I did a bad job word ordering. So I'm just going to continue on over here. And the proof of this is really straightforward and nice as well. if I consider the following, the unknot, and then this, what we call a pretzel knot, it's going to look like this. 3, 1, 2, 3, 4, 5. This. All right, so if I consider this knot, this is a Legendrian version of the, I think, -3, -5, and then I'm going to say -2n plus 2n minus 1. 2n plus 1 crossings here. This is a pretzel knot, and if I want to compute the genus here, I just need to find some pinches that get me down to the unknot. It's pretty easy to see where I pinch. Does anyone see where I pinch? So I see 2 red points here. And if I pinch there, then what I have is I have like an unknot with 3 twisty towers going up, and I can just undo those twisty towers with a bunch of Reidemeister 1 moves. So I see that the genus here is 1, right? And then what I actually do is I look at these as smooth knots, and I notice that the Seifert surface of these knots is actually exactly given by sort of these 2 discs and then these 3 sort of twisty ribbons connecting them. And in fact, what I can do is I can compute the Seifert matrix of these guys. Which is the matrix that I get when I think about the way that the homology generators of this surface link with each other. And using the Seifert matrix, I can compute the Alexander polynomial. And what I'll notice is that this polynomial is irreducible, it has degree 2, and it's unique for each n. And that means that if I take, what that means is that it can't, if I take 2 knots and I compute the Alexander polynomial of their connect sum, then that is going to be the product of their Alexander polynomials. And in particular, so let me call this Kn. I have that the Alexander polynomial of Ki connect sum Kj is not of the form f of t, f inverse of t. Sorry, not that. No, I think it's right. I'm trying to remember if the inverse goes here or here. But basically, I know that it can't be of this form, and that means that it's not going to be smoothly concordant. And if they're not smoothly concordant, then they're certainly not quasi-concordant, right? And so I get, if I take connect sums with these things, then I have my family, my sequence.
You sure the inverse is not on the T?
It might be on the T.
That was good one.
Yeah, sorry. What am I doing? Thank you. Okay. I think I'm actually out of time. So let me just state some other sort of properties of the metric monoid that I know to be true. So one thing that I know that's true in the smooth categories, if I take an fully amphichiral knot, and I connect summit with itself, then I get the unknot. Or I get something concordant to the unknot. That we can prove is not true here. There's also stuff that I know about sort of operators on knots in the smooth category. And those results we can replicate here. So for instance, if I have a winding number n satellite, I can show that that is always going to be a bounded distance away. And also if I have a winding number 1 satellite, winding number 1 satellite, I can show that that as an operator is a quasi-isometry on Legendrian knots. That being said, there's like still a ton of sort of easily posed questions or questions that we've brought from the smooth category we can ask here that we don't know the answer to. And that's where I'll end my talk.
When you're putting the metric monoid structure, is it up to Lagrangian concordance or Lagrangian quasi-concordance?
It's going to, so the classes I'm going to consider are Legendrian knots up to quasi-concordance, and then quasi-cobordisms are going to give me the metric.
So you said that it was only in dimension 3 that we know the construction of like a lambda plus.
Yes.
But in other dimensions, we sort of know it exists. Right?
Sorry, I said in R3,
yeah,
we know explicitly how to construct it, but in other 3 manifolds, we know it exists.
So does it make sense to do such things, even if we don't know an explicit construction?
We can definitely define this without knowing like an explicit construction. The other problem with working in other 3 manifolds though is that we just like know a lot less about those Legendrian knots at all. And so like trying to prove any results about them gets like pretty hard. Which is
and
why
that
we
would also be true in like higher dimensions.
Yeah, I think. Yeah.
Have you thought at all about this? I mean, I guess this Ian Egel thing about concordance, or sorry, so it's the statement is that concordance.
Ribbon concordance
is a partial order, and this statement, the way the proof is like something like proves that the fundamental groups are isomorphic by using representation varieties. Yeah. So I mean, I don't know. Is there any? I guess there's like obviously a lot of stuff you'd have to come up with in order to adapt.
Yeah. So there's this fundamental. So part of that proof is this fact that you have actually a complete invariant
from the non-fundamental group.
Yeah, for smooth knots.
Yeah. Whereas
we'd have no idea what a complete invariant of Legendrian knots would even look like. Right?
I thought we had like not contact homology.
But that's not invariant. I think it's the not contact. The statement is that the not contact homology of the conormal is a complete.
Yeah.
And even
it's a complete smooth knot.
It's a complete smooth knot.
But Legendrian knots, like for each smooth knot, I have infinitely many Legendrian knots, right? Because I can stabilize one way and I get a new knot, and I stabilize the other way and I get a new knot, and then I can build mountain ranges out of this. And sometimes the knots are simple, which means that they're fully classified by the smooth invariance, by the classical invariance, which is great, but often they're not. And there are knots that can't be distinguished by the DCA. And like, we just don't have anything that could do that job.
But it is true. Is it true that the complement of the Lagrangian knot is a complete invariant if to contact dimorphism, or is that not even true?
Knot.
So like if you look at contact S3 and you look at a complement, and we can talk about this later also. This is like, there's many questions in this kind of.
Yeah. I'm not sure.
Okay.
Yeah.
Any other questions or comments?
You're sharing it. Sorry.
No. Do you have any other questions or comments?
I do. can talk about them after.
All right, so we thank the speaker again. Thank you.